So let's look at a couple examples here where we have to use washer cross sections to find a volume. The formula again is going to be this right here. So notice that when we're using the washer method, we have two radii because we're going to end up with a hole. So this is the radius of the outer part. This is the radius of the whole part. And we'll subtract the square of the bigger radius minus the square of the smaller radius in terms of x or y if we're integrating with respect to y. So we have a picture that looks very similar to previous problems, and actually we're going to use the same region as we've used before, but we're going to rotate around somewhere else now. So we're still looking at this region here bounded by the square root of x, the x-axis, and x equals 1, but now we're going to revolve around the y-axis. Who can explain why this revolution here is going to give us a hole, or why we need to use the washer method here rather than the disk method? What's the difference? So to decide whether you're going to use the disk method or the washer method, if the region doesn't make contact along the axis here, if there's a gap between the axis and the region that you're rotating, you're going to have holes and you're going to have to use the washer method. Over here, when we had the axis over here, the region touched that axis along the entire length of it, then you don't have any holes, you don't have to use the washer method. You could actually always use the washer method if you want. So the examples we've been doing with the disk method, you could use the washer method, but since there's no hole, what would the small radius be? 0. So if there's no hole, you could use the washer method still, you just have a small radius of 0. That's not going to be the case here though. So there's two radii we need to find in this picture. So first of all, let me ask this. Which way are we going to slice it, horizontally or vertically? We're going to slice it horizontally. So we're going to slice it up this way. And we do need to find two radii. We're going to find a big radius. That's going to be the outer part. And then we need to find the smaller radius. The bigger radius here is going to be this distance. So it's going to be the distance from this line x equals 1 to the axis of revolution. You guys may start noticing that the radii are always going to be the distance to the axis of revolution. So we just need to find this distance here. That's going to be our big R. Let me label that. Our small radius is going to be this distance. Okay, that's going to be the radius of our hole. So that's going to be little r. Can you read that? So what's the big R going to be in terms of y? Since we're slicing it horizontally, what's the big radius going to be in terms of y? I'm going to write it like this just so we remember. It's just going to be 1, right? You guys agree with that? Doesn't matter what y is, that radius is always 1. Now, the little radius, that's going to change. That's going to be a variable. So in terms of y, what's this little radius going to be? What is it? Y squared. We've actually seen this already. So we solve this equation here for x, because this distance here is x, but we need to write it in terms of y, so x equals y squared here. So we know what our big radius is, we know what our small radius is, now it's just a matter of plugging it into our formula. So the volume of this solid is going to be pi times the integral. We'll take care of the limits in a second. Big radius squared. What's our big radius? 1. So 1 squared minus little radius squared. Y squared squared, which will end up being y to the 4th with respect to y. Now, what is the lowest y value that we're going to use here? Yeah, we're going to start at 0, and we're going to go up to 1. One other thing before we evaluate, and again, I'm not going to spend time evaluating here, I'm focused more on setting them up, but we want to simplify this as much as we can before we evaluate. So this is going to be pi times the integral from 0 to 1 of 1 minus y to the 4th with respect to y. And this integral right here is going to give us that volume. In this example, we have the same region, I know you guys are probably getting sick of this. We have the square root of x. We have the x-axis and the line x equals 1. But now we're going to revolve it around the line x equals 3. So this line right here is our axis of revolution. I think it's obvious in this example that we're going to have a hole, because our region here that we're revolving does not touch this. It doesn't touch the axis here. So what we're going to end up with is kind of a donut shape, but it's going to have vertical walls on the inside, and it's going to be flat on the bottom. So flat on the inside, flat on the bottom, and rounded on the outside when we revolve this around. So since we're revolving around a vertical axis, which way are we going to slice it? Slice it horizontally. And we need 2 radii. What I like to do to find my radii, or at least draw in my picture where the radii are, is start at the axis and go all the way to the outer edge of your figure. That's going to be your big R. Then for your smaller r, small r, we're going to start at the axis and go until you hit the near edge of the figure. And that's going to give us our little r. So what is, since we're slicing it horizontally, we're still going to integrate with respect to y. So with respect to y, what is our big radius going to be? Yeah, so it's going to be 3 minus y squared. And the reason is this distance right here, let me put that in a different color. This distance right here, that's going to be y squared. So then the distance from the line x equals 3 to that point is going to be 3 minus y squared. So it's the bigger minus the smaller. I'm just subtracting the x values. So the x value here is 3, the x value here is y squared. So the big radius is going to be 3 minus y squared. The small radius is going to be what? 2. That's just going to be the bigger x value minus the smaller x value. This x value is always 1, this one's always 3, so it's 3 minus 2, always. Doesn't depend on what x is, or what y is, sorry. Now I'll just take that and translate it to the formula. So the volume of our solid of revolution is going to be pi times the integral. We'll take care of the limits in a minute. Big R squared, so we're going to have 3 minus y squared squared minus little r squared, 2 squared, with respect to y. And since we're moving along the y-axis, what's our minimum y value going to be? 0. And the maximum? 1. I don't want you guys to start thinking that our limits are always going to be 0 and 1. That's just the case in the examples we've been doing here. The limits could really be any values here. Again, our goal here was to set up the integral. You could simplify that integrand, the inside of the integral, and then evaluate that. You would have to expand this part here. That would be 9 minus 6y squared plus y to the 4th, and then minus 4, and then evaluate that integral. And that'll give you the volume.